My name is Dejan. I will show you some things about our little quantum computer that you've seen some of it last week, but since we're waiting for the presenter, I can show you some more. For example, how it actually looks. Okay, this is a webcam picture. The whole thing is, oops, have a problem. Okay. Uh, I'd like to show you the not just the screen, but the actual hardware inside. What you can see here is a strong magnet and a little sample inside. This will be difficult to. You only see the cover of the little tube. The tube contains diluted substance with won't go too deep into the technical details, but a particular molecule containing phosphorus and hydrogen, and the phosphorus atom is the one of the quantum sites, more precisely the nucleus of the phosphorus atom, and one of the hydrogen atoms in the molecule is the other qubit. Of course, we don't have just one molecule. We have an enormous number of them. But the trick is that they all work in unison. They are effectively we try to put them in the same quantum state, and the large number of nuclei operating in this manner allows us to have a stronger signal. And the bottom line is that the computer can operate at room temperature. It is still very sensitive to temperature variations, but it doesn't need cooling to near absolute zero. Since I'm moving the camera, I can also show you some of the electronics, the little blinking lights that indicate the pulses sent to the core. And the driver circuitry for the magnetic coils. Okay, there's reflections. I don't know how much you can see. Maybe I'll share some photographs later on Discord. Can anybody hear me? No?
Yes, we can hear you.
Okay. So maybe we go back to the main screen. Still, I'm trying to establish a direct connection so that we could cast the screen, but unfortunately at this moment we're still looking through the webcam. Zoom, can I see the, how can I see this? Okay, yeah, oh yeah, the focus is, about the best we can get right now. Hopefully at the end of today's meeting, we'll have a screencast and the picture will be better. The machine is, you can probably see it is doing a calibration, and this is related to previously mentioned sensitivity to temperature. We have an interesting weather in copper these days, and apparently the changes, even though the office is heated and controlled, still destabilize the coherence of the signal. So we're still running the calibration, and that unfortunately prevents me from showing you the more interesting screens. For example, how we compose the quantum gates and how we run the program. The calibration should end in 2 to 5 minutes from now. Meanwhile, uh, well, unless I abort the I guess I could abort the calibration and show you some stuff. Or are we ready to start the main lecture? And no, in Slovenia, uh, uh, near the on the Adriatic Sea. Okay, maybe I could. Okay, this is a screen indicating the calibration in progress, but I'll try to show you something more interesting. This is the screen I showed last time. It's the screen on which we compose a quantum circuit or a program. Uh, the way it looks is actually very similar to the Qiskit visualization. We have two lines, horizontal lines that represents the two qubits. The first one is, you can, I think, just barely read Q0 and Q1. And on each of these lines, we can place gates from this menu of gates. For example, we take an X gate, which, as we learned, is a knot, and place it on the first qubit. And then, for example, we can take a controlled knot, place it on the second qubit, and connect it to the first one so that the qubit 0 is the controlling input of the Q naught gate. Now, no, the calibration is not complete, so I cannot, unfortunately, I cannot run the program. But perhaps I can show you some of the sample circuits from the library that was built before.
Can we just show the computer, the SpinQ, which now we are able to see it on the screen?
Okay.
No, it's much more easy to see what is happening on the screen of the computer, no?
Yes, it's pretty clear now.
So they are prepared. Just one example, the other for tomorrow, okay? Cadê? Bem lá. Mas ti hoje,
Не вем, мам.
ker govori po angliško, da
Basically, I'm not sure if my microphone is on. Can anybody hear me?
Yes, we can hear you.
Okay. I'd like to show you the screen again, basically, because we fixed the link and now your eyes can rest. You were able to see things as they were meant to be seen. And I'll just show one example from what we did in the lecture. The double Hadamard gate on 2 qubits with the C naught in between. This is the circuit diagram, much like in Qiskit. And this is the result of the run which was performed earlier. So it's already processed. We see that the expected 1-1 state has a probability of slightly over 90%, and the 0-0, which shouldn't be there, has a little under 10% probability. As I mentioned earlier, we had some problems with the calibration, and these numbers would be closer to theoretical if no, I really don't want to run a long time because you're probably all tired and we, uh, we are late running late, but I wanted to show you another one, pre-prepared, let's say, example of tasks that were now executed previously. Namely, yes, this is, since we're talking about machine learning, this is effectively a neural network on 2 qubits. It's won't go into the details why, but you see the typical rotation operators that you've seen in the lecture. It looks quite colorful and quite complicated. And this is the result of the run. It's mostly the one state.
Pohvali Kitajce za knjižnico.
I didn't understand that.
Pohvali Kitajce za knjižnico.
Oh yeah. This example came with the manufacturer of the computer, the SpinQ company. It's so can't even say that I fully understand how it works, but you can see the basic characteristics. With that said, I would like to finish and we'll try to show some more examples tomorrow. Take care, Dali.
It was all from our part.
Thank you. Yeah, now it's more visible and looks really pretty interesting. So, yeah, tomorrow we will see the bigger demonstration. So don't miss it up.